So today I have the great pleasure of hosting Tom Willey, Mr. Tom Willey, who will be sharing on soil's outsized role in Earth's age-old carbon trading scheme. Tom Willey, along with his wife Denesse, operated T&D Willey Farms from 1981 through 2016. It was a 75-acre certified organic farm in Madera, California, growing a wide array of Mediterranean vegetables year-round. T&D Farms, T&D Willey Farms produced produce was appreciated in specialty markets and fine restaurants up and down the U.S. West Coast, as well as on the tables of over 800 weekly CSA, Community Supported Agriculture, subscription members in their own community. Tom was, for nearly a decade, Slow Food USA's governor for California's Central Valley, and he passionately advocates for local food prominence through his writing, speaking, radio, and event organizing activities. His monthly Down on the Farm conversational radio program features the work of progressive farmers and others prominent in San Joaquin Valley's agriculture and food communities. Tom has served over the years on the boards of directors of the Ecological Farming Association, California Certified Organic Farmers, and until recently, a member of CCOF Certification Services, 5-person LLC Management Committee. He currently serves as a policy advisor to the Cornucopia Institute, which monitors integrity of the U.S. organic industry. He has been collaborating with several California organic growers to develop no-till and reduced-till organic vegetable production systems over the last several years. We're very lucky to have you and all your experience here with us today, Tom. So thank you for making time to put this presentation together and share it with us.
Thank you, Margaret. My pleasure. So are we ready to go then?
Go ahead. Does it look good on your end?
Yeah. We got pictures down the side of other people. I don't know if you want to just put my picture up on top or something like that, so it doesn't obscure the slides. But maybe it doesn't look like that to other people.
Yeah, it might just be your screen. It looks good on my end. Did it look good to anyone else? Everyone else? Okay, we have a thumbs up.
Okay.
Looks good from my end too.
We'll go for it. Okay. So carbon is the currency of exchange within soil's biological food web. Plant leaves absorb carbon dioxide from the air. Now my slides aren't advancing.
You could try an arrow or the space bar.
That's sometimes what I'm doing.
Yeah,
it was working just a little bit ago.
On the screen, sometimes it'll pop up like a little arrow in the bottom left.
There's a little pencil down there or something, but gosh dang. There we go.
There you go. Okay.
All right. We'll start over again. So carbon is the currency of exchange within soil's biological food web. Plant leaves absorb carbon dioxide from the air, water through roots, and employ the sun's radiant energy to manufacture sugars. This photosynthetic miracle supplies the chemical energy that supports virtually all life on Earth. Carbon has been getting a bad rap of late, quite undeservedly. Though it might be otherwise somewhere else in a boundless universe, carbon is the latticework of life on this rocky planet. Take any form of life on planet Earth, squeeze all the water out of it, and what remains is 50% pure carbon. Atomic 6's propensity for kickstarting life is colorfully described by Bill Bryson in A Short History of Nearly Everything. What sets the carbon atom apart is that it is shamelessly promiscuous. It is the party animal of the atomic world, latching on to many other atoms, including itself, and holding tight, forming molecular conga lines of hardy robustness the very trick of nature necessary to build proteins and DNA. Earth's carbon was forged deep within aging stars, much older than our sun, in a process called nucleosynthesis, a sort of alchemy by which hydrogen begets helium, then successively every other element on the periodic table. The life-enabling carbon thus born that found its way to our Goldilocks planet continuously cycles between 5 reservoirs: Earth's atmosphere, soil, which harbors 3 times the quantity of carbon as our atmosphere, living biomass, the surface oceans, where carbon exchanges readily with the air above, and then ocean depths and beyond, where 99.9% of all carbon on Earth is sequestered, stores that only re-enter active reservoirs over millions of years. But of course, that presumes that we're not digging these up and burning them as fuel. I proposed a question to an audience of some 200 consulting agronomists some years back. How many of your grower clients would list carbon as an important input to their farming systems? As I proceeded along the Sodom and Gomorrah countdown, nary a single agronomist suggested that even 1 in 10 farmers might appreciate carbon's role. And I'll admit, shamefully, that it took about 3/4 of a 40-year farming career to get my head around the fact that we farmers are simply manipulators of photosynthesis, gathering carbon and bending it to our needs and purposes. Everything else we do is subservient to that process. Besides fueling their own growth and reproduction and our harvests, how else might crops employ the products of photosynthesis? Well, it turns out that plants can leak as much as 40% of their total biomanufactured sugars, along with organic and amino acids, etc., into soil that surrounds their root tips, essentially feeding and farming microbial allies, an arrangement Australian soil ecologist Christine Jones describes as the very first carbon trading scheme. Well, what are plants bartering all of this hard-earned candy for? An astounding diversity of soil microbes reward their leafy benefactors by cycling and safeguarding vital plant nutrients, building soil architecture that is receptive and retentive of water and oxygen, suppressing plant diseases, and degrading toxic pollutants. Lawrence Livermore National Laboratory's Soil Microbiome Scientific Focus Team writes, the soil microbiome is the most biologically diverse community in the biosphere, holding at least 1/4 of Earth's total biodiversity. Tens of millions of species of bacteria, archaea, fungi, viruses, and microeukaryotes exist below ground, although only a few 100,000 have been characterized in detail. A single gram of surface soil can contain more than 1 billion bacterial and archaeal cells, trillions of viruses, tens of thousands of protists, and 200 meters of fungal hyphae. Well, what role do each of these myriad species of soil-dwelling bacteria, fungi, archaea, nematodes, and protozoa contribute to plant growth and health? The short answer, we don't know, at least not much beyond a newfound understanding that almost all of these countless soil organisms are not only beneficial, but essential to the life-giving properties of soil. Well, Jerry Hatfield, the retired director of USDA's National Laboratory for Agriculture and the Environment, stuns audiences with the fact that the top 6 inches of an acre of healthy soil hosts a microbial biomass equivalent in weight to a pair of adult elephants. When microbes, living and dead, embody 50% of total soil organic matter, their plant neighbors understand that at the table of life, microbes always eat first. We farmers should equally appreciate that. Feeding microbes builds soil organic matter. Mediterranean California's mineral soils, in their pre-agricultural state, moist in the winter, dry in the summer, range between 1/2 and 2% organic matter. Sandy soils in California's warm interior tend lower, while clay soils near the cooler coast approach 2%. In retirement, I've enjoyed the privilege of engaging with a group of legacy organic farmers, doing on-farm research into no-till and reduced-till organic vegetable systems. Our 3 cooperating farm cooperators have practiced exemplary husbandry on the same soils for over 3 decades, annual compost application and cover crops, and in one case, grazing, resulting in soils that measure from 2.5% to as much as 5% soil organic matter, double the carbon content of neighboring fields denied these inputs. A 19-year University of California study comparing 3 farming systems under tillage demonstrated that only the annual rotation, including both compost and winter cover crops, increased total carbon, measured 2 meters deep over the period. Note that it is rare but essential that soil carbon studies sample subsoil to at least 1 meter depth. Early claims that no-till alone increases soil carbon were based on shallow sampling no deeper than the first foot. Studies at depth suggest that increased surface carbon in chemically farmed no-till fields is offset by gradual declines in the subsoil, a redistribution, not an absolute increase through the profile. Another 8-year study conducted at USDA's research farm in Salinas, California, confirms that frequent cover crops and compost additions can drive soil organic matter accumulation, even under conventional tillage. Though stabilized carbon in compost drove soil organic matter increase, the more microbial available carbon in cover crops or fresh meat for microbes drove greater nutrient cycling and higher crop yields. So you see here that they have 4 different systems or 5 different systems here. One was no compost and a legume rye cover crop every 4 years. Then they have an addition of compost with the legume and rye cover crop every 4 years, and that pops up the carbon in the soil. But system 3 with the annual compost and the legume rye cover crop every year is the champ, and increased carbon, soil carbon over the 8-year period to the highest degree. And then this is a mustard cover crop, and then this one was the just the rye. So it takes, like it did in the UC Century study, it takes both cover cropping and compost additions to significantly increase soil carbon over time, as it did on the 3 farms that we work with in the no-till project. So in Bismarck, North Dakota farmer Gabe Brown, regenerative agriculture's poster boy, reports extraordinary increases in soil carbon over a 20-year period since his adoption of no-till in 1993. Gabe stair-stepped into incrementally higher organic matter plateaus by adopting wider crop rotation, cover cropping, and then multi-species cover cropping, and finally ruminant grazing integration over the 2 decades. Though not a university researcher, Brown has opened his farm to significant scrutiny by scientists over time. His 11% organic matter claim begs the question as to whether there might be upper limits on soil organic matter accumulation in mineral soils. USDA's Sustainable Agriculture Research and Education SARE program states that sandy soil measuring 2% organic matter is exemplary, while clay soil at 2% would be considered deficient. SARE guidelines for farm soils put organic matter upper limits around 3.5% for sandy soil and 6% for clay soil. Compost is both poorly available and uneconomical within the context of U.S. corn and soybean producing regions. Gabe Brown and other regenerative innovators model carbon-rich Midwestern prairie systems under the influence of bison grazing. Their management-intensive ruminant grazing practice appears to adequately substitute for the compost used in high-value specialty crops. At T&D Willey Farms in the San Joaquin Valley's Madera County, we successfully maintained 2% organic matter in a fine sandy loam, growing year-round vegetables by annual applications of compost, averaging 15 tons per acre over 2 decades. Note that our farm laid 4 years in undisturbed fallow prior to our purchasing it in 1995. I regret to say that we did not employ cover crops, even when agronomist Ralph Juergens urged me to grow my own carbon rather than pay more money for it in his compost. But we were harvesting $3 million worth of produce from 80 acres, employing 50 people year-round, and I didn't have the ground to spare. It is useful to think of your soil as a car's battery or as your checking account. Plants transform CO2 into chemical energy through photosynthesis, continually charging the system with root exudates, while soil microbes consume much of that energy to mineralize nutrients from organic matter for their own needs and for those of plant allies. Charging versus discharge must remain in balance or favor charging. Otherwise, the system runs down. Similarly, you must make deposits equal to withdrawals from your checking account to keep in good graces with the bank. According to scientists, humanity has overdrawn our soil carbon account by 133 billion tons since the invention of agriculture some 12,000 years ago. According to soil scientist and World Food Prize laureate Ratan Lal, from agriculture's dawn until the late 1950s, tillage or plowing released more soil-stored carbon into Earth's atmosphere than had all the burning of oil and coal since the Industrial Revolution. Converted to CO2 emissions, that's north of 450 billion tons of carbon dioxide. So it's important to get your head around a little bit of math in this business. As we mentioned before, that all living things squeeze the water out of remain 50% carbon. Now that includes your soil organic matter if you dry it down. and take all the moisture out of it, it's a bit over 50% carbon as well. And soil can be, carbon can be expressed as soil organic matter that I think we farmers are more comfortable with or used to, but sometimes by scientists, it's expressed as carbon and not as soil organic matter. So when you're talking about carbon dioxide equivalents of your soil carbon, then you need to understand that CO2 is one carbon atom and two oxygen atoms. A carbon atom is an atomic mass of 12, oxygen atomic mass of 16. So you got 12 plus 16 plus 16 equals 44. And so the ratio of carbon to oxygen in an atomic, in a CO2 molecule is 3.67 to 1. So to simplify it, you can just use a factor of 4. So if somebody expresses your soil carbon as a certain number and you want to know what the CO2 equivalent is, you just multiply that by 4. Pretty simple, but took me a while to get my head around it. Anyhow, altogether, our planet breathes in photosynthesis and out respiration around 200 billion metric tons of carbon, 700 billion tons of CO2 through its natural carbon exchange cycles every year. And as you can see in this video, the greening is photosynthesis, and in the blue is the oceans. 50% of photosynthesis occurs in the oceans, 50% on land. And this is the pageantry over a year's time of how the planet breathes in and breathes out carbon dioxide, and breathes in and breathes out most of it. So this NASA image shows the exchange of carbon between on land and in the oceans, about half of which occurs on both sides. Half on land, half in the oceans. Human activities, including agriculture, emit another near 10 billion tons of carbon, or 40 billion tons of CO2 to the atmosphere yearly, just under half of which is mercifully reabsorbed through natural systems. So in these images, they're expressing things in terms of carbon. So they say this was a few years ago when we were only doing 9 billion tons of carbon, which was about 36 billion tons of CO2 equivalent. And now we're up to 10 and 40. So you got to know what numbers are thrown at you and what factors to modify them by. The remainder of the carbon that humans emit accumulates in Earth's atmosphere where it is responsible for significant climate mischief. When agriculture, through both cropping and grazing, conscripts 40% of the planet's dryland surface, our contribution to the problem and its potential solutions is outsized. Intensifying photosynthesis is the simplest and the cheapest means of removing atmospheric carbon. And remember, farmers are merely managers of photosynthesis. If we cause more carbon to be absorbed into our systems than they emit, our soils will safely tuck extra carbon away where it once belonged, at least for a while. Indigo Ag is the primary marketer of soil carbon offsets, but currently restricts enrollment to farmers in the corn and soy Midwest and the South, where their models of estimation have been developed. Farmers who adopt practices leading to soil carbon accumulation report receiving about $15 per acre and never more than $30, according to one Illinois farmer friend. Though there are some happy campers, farmers surveyed by academics express frustration with low pay price, high paperwork burden, hocus pocus credit calculations, bias towards large scale operators, and greenwashing. Indigo is selling offsets to greenhouse gas emitting industries for $40 per ton. So here we're into another calculation business. This whole carbon trading industry works off of CO2 equivalents. So in the case of methane, which is contributed to the atmosphere by agriculture, either through animal ruminant agriculture or through paddy rice agriculture, or maybe even if your soil gets saturated in a flood for a period of time over the winter, you might be emitting some methane. The equivalent of a kilogram of methane to the CO2 equivalent is 25 times. Methane is 25 times the equivalent of CO2. You would think initially that would be a factor of 85 because methane is 85 times more warming than a carbon dioxide molecule in the atmosphere, but it only persists for about, I believe it's about 25 years compared to 100 years for carbon dioxide. So that gives it a discount factor down to 25 to 1. In the area of nitrous oxide, which is emitted from soils that are fertilized with inorganic nitrogen mainly, and to some extent from organically fertilized soils as well, the factor is 298, almost 300 times the equivalent of CO2 molecules. So nitrous oxide, if you can prevent a kilogram of that or a ton of that from emission and prove it, you could get a lot of credits for that. So Indigo is selling offsets to greenhouse gas emitting industries for $40 a ton, a CO2 equivalent, paying farmers $30, a 75-25% split. Measuring soil carbon, particularly at large scale, is difficult and uncertain. When you appreciate soil carbon's dynamism envisioned as a battery, again, or as a checking account, Indigo Ag's claim to purchasers of offsets that carbon has indeed been added to a farmer's field and will stay put for 100 years is hard to believe. According to Gabriel Popkin, writing in the journal Science in 2023. Though Indigo states that cylindrical cores pulled from fields are the gold standard for measuring carbon in soil, the company only extracts these to a depth of 1 foot every 5 years on 10 to 30% of participating farm fields, creating a predictive model from which to operate their whole carbon trading scheme. Colorado State University soil scientist Stephen Ogle, a developer of soil carbon models, says that their margin of error can exceed 100% for individual farms and even state-sized regions. At T&D Willey Farms, we pulled 1 foot deep soil cores annually over 2 decades, each exacting location representing a 10-acre paddock of our 80-acre Madera farm. These graphs show that annual fluctuations of 0.5% were common, and sometimes wild, unexplained deviations could pop up on soil managed consistently from year to year. The U.S. Department of Energy's Roads to Removal report, published in December 2023, states that the durability of soil-based CO2 storage is highly uncertain, while at the same time endorsing soil-based CO2 accumulation in croplands as low energy, low cost strategy to reduce atmospheric CO2 concentration. The Department of Energy's report aims to intensify photosynthesis on farms by incentivizing cover crops, perennial field borders, and perennial carbon crops where appropriate. USDA's recent Census of Agriculture reports that a mere 5% of the nation's farmlands are currently cover cropped. This Department of Energy map indicates that $40 per ton carbon dioxide equivalent stimulates very little cover crop adoption in corn and soy country, compared to $100 per ton that farmers are yet to see. It would move the needle even less in specialty crop regions like California. If soil carbon credits are unlikely to make you rich very soon, should you just forget about building soil organic matter levels on your farm? To the contrary, building soil organic matter will pay you benefits over time that will far exceed any trading carbon for dollars shell game. Soil organic matter is widely recognized as a key indicator of soil properties associated with higher fertility. It enhances aggregation, soil structure, infiltration of rainfall, and optimum air-water balance. Our group of farmer experimenters learned from several expert tutorials that the top foot of a 2% organic matter soil harbors some 4,000 pounds of organic nitrogen per acre within the living, the dead, and the very dead fractions of solar energy stored as organic matter. Synthetic and biological nitrogen have different identifying isotopic signatures. Tracing nitrogen isotopes through plant-soil interactions has revealed that crops acquire half of their total nitrogen from soil organic matter without regard to how much synthetic nitrogen they have been supplied. Besides being a super nutrient storehouse, each 1% increase in soil organic matter stores an additional 20,000 gallons of water within an acre, 6 inches of soil. William Albrecht, early 20th century pioneering soil scientist and chairman of the Department of Soils at the University of Missouri, appreciated soil carbon's foundational role many decades ago, as evidenced by his essay in the USDA's 1938 Yearbook of Agriculture, Soils and Men. Attempting to hoard as much organic matter as possible in the soil, like a miser hoarding gold, is not the correct answer. Organic matter functions mainly as it is decayed and destroyed. Its value lies in its dynamic nature. So thank you. Hopefully we've stimulated some interest and questions and challenges to some of the BS that I've thrown at you here. And so I'm open to that from all quarters.
Wonderful. Thank you. You're getting lots of claps if you can see them floating across your screen. All right. So very stimulating, Tom. Let's see what questions we have from our guests here. You can raise your hand and come off mute and share your question or discussion points, or you can write it in the chat. I think you had us all captivated.
Tom.
Yeah, Frank.
So these guys are trading carbon credits as if they're trading real money. But you pointed out that they're not really keeping good accounts of the currency. So how's that all going to work out? People are getting credits for, storing carbon, but the carbon's not staying there. So
yeah,
how's that going to work out?
I think it's really a scam, and it's a way that we can waste billions and billions of dollars thinking we're improving a situation that we're not really improving. So I would actually advocate incentivizing or paying people to do practices like adding compost or doing grazing or doing cover cropping, knowing that over time those practices will lead to, improved carbon storage in soil. So, yeah, I don't think it's very smart scheme, but people are, you know, uh, doing that both with soil and then in other areas around the world with, forests in Brazil and all this sort of thing. But it's not very real. Uh,
That's disheartening.
I don't think much of that is going on in California because, like I say, the kind of money that they're paying farmers to demonstrate that they're building carbon soil, it's just not significant money in the West for where we do specialty agriculture. Yeah. So, I mean, 15, 30, 40 bucks an acre in the Midwest can double your profit in some cases on, corn and soy, but California, that's not the case. So it's not really that a significant issue out here at the moment. Yeah. Margaret, if we don't have any more questions immediately, why don't you put up one of those other two images that I sent you in?
Great.
We'll talk about.
Okay. If you want to stop sharing your screen, Tom.
Okay, I'll do that.
Great. And then which one do you want to see first?
Either one is fine. The soil aggregate is fine.
Great. Here you go.
Okay, so there are some folks who I respect. I have a quote from a great soil scientist somewhere who I've forgotten the name of, that the greatest measure of soil health or soil functionality is the percentage of stable soil aggregate. So this is a blown up image of a soil aggregate, and one of the things that I've learned about it is that each soil aggregate is almost like a planet in a solar system. They can have very different species. They can have very different resources in them, which attract different species of organisms. And the most fascinating thing I've learned about them is that they're oxygen rich on their exterior, but in their interior, they are oxygen poor. They can be anaerobic. And that creates different situations in on our farm. We had the most difficulty with uptaking only one micronutrient, which was manganese. And I've since learned that manganese can only be uptaken by plants in a reduced form. So that can happen in the anaerobic core of a soil aggregate, whereas on the outside, manganese is oxidized and is in a form that plants can't uptake it. So there's a lot of interesting things. Um, this is a mycorrhizal fungal hyphae, which is much thinner than a root. And as we know that mycorrhiza can be an extension of a plant's root system, that can magnify the root system by a factor of 10. Because of the tight spaces in these aggregates, a mycorrhizal hyphae can get in there and interact with this system, whereas a plant root is the diameter of it is too great and can't penetrate into the interior of one of these aggregates. Also, organic matter fragments can be incorporated in these aggregates, and it's just a fascinating world that is almost like a planet. And so we're learning that the heterogeneity or the variation in species and microbiome within aggregates can vary tremendously, and aggregates can be as large as a grain of sand, or maybe even macro aggregates can be as large as maybe a ping pong ball. But a functional aggregate can also be of a diameter of the human hair as well. So when since I've been on the Central Coast since retiring from production agriculture in San Joaquin Valley, I've been looking at these beautiful clay soils over here that are super productive. And yet sometimes farmers over here will abuse the hell out of them. They'll turn plow them and turn up a whole field that looks like a bunch of roof tiles shining, because it's pretty wet soil when they're doing that. And you go like, how in the hell can they beat soil up like that and then turn it into a seed bed and produce the beautiful crops that they do over here? But when you appreciate the fact that a functional soil aggregate can be as small as the width of a human hair, and you realize that all they're doing a lot of destruction, they can't completely destroy the value of these soils. And so it's pretty amazing that that soils feed us as well as they do, as tremendously as we abuse them at times.
Tom, we have a question from
Okay.